Yeah.
How much percentage is get?
All right. Oh. Did you have a test? You didn't have the exam yet? Okay.
What?
I thought you had the exam for some reason. Okay. Never mind. All right. Questions about anything related to the homework or class? I mean, I gave you, so far we've covered capacitance and we've covered resistance. Basically, the techniques are the same. An assumption is made either charge or current, or sometimes you're going to assume voltage. Then you go through the steps, calculate the D field if it's charged. After you have the D field, you get the E field. After you have the E field, you get the voltage. And then, it's really capacitance is simply Q over V. For resistance, you assume current usually. Calculate J, current density. Calculate the E field, integrate the E field over whatever the length is of the resistive ends. And then you simply take V divided by I to calculate the resistance. Now, are there any questions related to this? I gave you, you got a fair number of thoughts. Anything else? Yes?
Could you go through 3.75 and how to work that one out?
Absolutely. Where did all my markers go?
Oh, wait, actually, I had about that. You put in the homework to do 3.57. Was it supposed to be 3.57 or 3.75? From the problem.
Well, it would be ones related to capacitance. So I'm not sure which one that is.
Okay, 7.5.
Can you tell me what the problem is you want me to do?
Yeah, I was just making sure I didn't actually do the wrong one.
I need.
Okay, so capacitor.
What? This is 3.75.
Yes.
3.75. Go ahead.
A capacitor with non-parallel plates is shown in the figure, and it's just like it's just one slide. One thing. I'm sorry.
No, that's all right. Is this the one with the curve? It's in cylindrical coils or spherical? I'll take it. Hold up. Give me 1 second. No, I mean these are good questions. You said 3.75?
Yes.
All right. Now this is, class, I want to tell you this. What Dr. Whitworth's book's doing is going through the same basic procedure for spherical, cylindrical, and planar surfaces. This is going to be a cylindrical surfaces. So try to understand this. I'm going to show this is the x-axis, this is the y. And then the way he has this is, he has a couple of plates. Let me see if I can draw this a little better. So what he does is this. He has down here, we have a plate. It's just a plate. And this distance to here is A. And I believe this distance to here is B. Is that correct, class? The way he shows it? Now he has another plate. And it's off at an angle. But this is still a radius A here, and this is still the distance b. In other words, they're the same exact length and dimensions, two plates, and they're separated by an angle phi. Now here's what this really is. Imagine you have an infinite plane that has a width from b to a, b minus a. Assume the distance from here to here is b minus a, okay? Think of that down here, and then this is going to be infinite in this direction. Then you have another plane, infinite in this direction, at that angle. You all follow me? Now we're going to get the capacitance per unit meter. Y'all with me? There's a couple of things that are hard to see at first, but you will see them. This is a typical cylindrical coordinates problem that's given a lot. Dr. Bashir, I think, gives this kind of stuff a lot. He teaches. So, if you think about this, if these are two plates, the voltage difference between this plate and this plate, if you think of this is, say, is V naught. Matter of fact, let's do it the other way. It'll be easier to see. Suppose we make this plate have a voltage of V naught, and make this plate be grounded, right, or 0 volts, right? Remember, those are electrically conducting surfaces. They're perfect electric conductors. They cannot have a voltage difference on them. Did everybody follow? Now, if you look at this, I'm just going to show you something that will really help you. The electric field lines are going to be in the azimuthal direction. Now, I'll talk more about this in a second. And we're going to neglect what's called fringing that I'll explain. So the electric field lines or streamlines would be like this. This would be a streamline. This would be a, I don't know if he shows this in the book. This would be a streamline. This would be a streamline. And all these things, there's an electric field, but the further out you go, the less the electric field magnitude is. And here's why. When I integrate the electric, it will be in the phi direction. I'm going to tell you this, and I'll get to this more in a second. When you integrate from here to here, E dot dl, from this point to this point, you have to get the same voltage as here, from here to here. You all see this? Well, this is a shorter path. That means the electric field here has to be higher. How many understand that? So this is one where I'm going to, I don't know how the solution is used, to be honest. But I want to make sure you get that insight. Y'all understand me on this? Now there's something else. Is there anything in the book about neglecting or ignoring fringing fields?
Yes.
All right, here's what a fringing field is in essence. I've said that the electric field, like if you had a planar capacitor like this, just a planar capacitor, and you put a voltage, say V naught on this, and you grounded this, I'm trying to make it as simple as possible. In the center, you can see the electric field would be straight down. Do y'all follow me on that? That's V naught, that's 0 here. The electric field goes from the higher to the lower voltage. This would be the direction of the electric field. That would be called a streamline. It's an actual trajectory of the electric field. But right at these edges, what happens is you get this kind of behavior. Now the electric field will actually, when it maps on that side, if you solve the actual equations, it's not going to be just straight down. Y'all follow me? That's called field fringing. Normally, we neglect that in most capacitive problems, and here's why. About 99.99% of the electrostatic energy that we'll get to today, hopefully, is between between the plates. There is a small, very small amount of fringing fields, but usually it's insignificant, okay? So when he says neglect the fringing fields, he's talking about neglect the fields that are not in the phi direction. Do y'all follow me? How many understand that? Now, this is one of those problems, we're not going to assume Q, we're going to assume V. And the reason is because if you assume Q, let me say something. The charge density here, and you'll see this in a second, at this point, is greater than the charge density out here. And I'll get to the reason for that in a second. Actually, we're going through something today called boundary conditions that will give you a lot of insight to this. But you've had some of this already. Does everybody follow me with the problem, what it looks like? So now, what I'm going to tell you is the E field, based on what he says, The E field is just going to be some value, and I'll just call it, well, I'll call, let me do it this way, because I don't want to confuse you with anything on this. I'm going to assume that the electric field is only in the phi direction, so that means it's just a phi component, okay? With me? Now that E field magnitude will be a function of the radial distance. So if we measure radial distance at any point here, we're going to have an electric field that's here. Do y'all follow me? It will be in the phi direction. Now the phi direction, the way you get this, just take your thumb, put it in the direction of the positive z-axis, and your fingers basically are pointing in the phi direction. Do y'all follow me, class? That's what it is, circulating, all right? So I'm going to say that this E phi right here is going to be something where I know the first condition is the integral of E right here dot dl, and I'll say from plate 1 to plate 2. So I can call this, well actually, yeah, I'll call this plate 1 and this plate 2. And plate 1 to 2 here is going to be V naught. Now, I'll try to explain this. I don't even know how he does this in the book exactly. But if that's the case, when we look at this integral right here, I'm assuming the E field is just in the phi direction. So what this really is going to be is the magnitude of the E field on this, I'm just going to go to the other one, trajectories, and it's going to be E phi dot dl. dl has to be in this direction, or dl here is going to be equal to, well, it's proportional to the radius rho. It would be in the d phi direction, or I'm sorry, rho d phi in the a phi direction here. If you look at this, remember rho d phi is the Viper on length. Y'all with me? And it's in the a phi direction would be the differential. I could write all the differentials there, right? I could write d rho a rho and dz a z, but the dot product when I do with the E field will only result in a d phi integration. So I come over here and I can see that when I take this integral of E, whatever it is, right here, and E is going to be a function of rho, and it is in the phi direction. And then I have times rho d phi here. The a phi components will dot out equal V naught. You'll see this in a second. And I go from 1 to 2 right here. Really, it's a d phi integration, so the phi goes from 0 to the actual value of whatever phi is. Does he give you a value for phi in there, or just leave it arbitrary? I wish I was a little clear here. I'm going to try to make sure I'm clear in a second. Anyway, this right here, E, is a function of phi. It's in, phi direction. It's a function of rho. We're going to figure out what it is in 1 second. Nothing in here depends on phi except d phi. You all see that? When you integrate that, you get phi evaluated from 0 to whatever the phi value is. So that means this right here, V naught, is equal to E in the phi direction as a function of rho. And then it's going to be times rho, and it's really times phi. And phi is nothing more than the angular difference between those two plates. Now, that means that E, I've got phi here. E of phi right here is equal to simply the voltage that was assumed, V naught, and then it's divided by rho and whatever the value of phi is. That's E phi. Okay, we started, this one's a little tougher, and I'm gonna love with you, it is. We started by assuming a voltage in this case. Do y'all follow me, class? This is one of the few you have to assume a voltage. You can't assume charge because the charge density is not constant over those plates. So we assume a voltage, then we determine the electric field's characteristics, assuming there's no fringing or be in trouble. Then after we have that, we get the D field. Y'all follow me? So if I have this as the E field, what is the D field? Does it give you a dielectric other than epsilon naught? We'll assume it's epsilon naught, okay? We'll talk more about this stuff. So to get the D field, what do? Well, we know D is equal to what? Epsilon E. You agree with that, class? All right, that means the D field will be in the phi direction, and I'll call it epsilon naught times E, which is simply V naught over rho, and there's a phi component. I'll put the phi out here because that's an actual angle. So that's the D field. Now something I haven't covered yet, and I'm glad you asked this very question. How many know if you have a D field and it is normal to a conducting surface, remember, this right here is a perfect conductor and this is a perfect conductor, right? How many know what D normal is with respect to the charge density? Anybody? Think of the units of D normal or D field. It's coulombs per meter squared, right? What are the units of charge density? Coulombs per meter squared, aren't they? As a matter of fact, and we'll talk about this, the D field on this surface right here, I'll put it here, D normal is equal to rho s, and that's true on a perfect conducting surface. It's not true for a dielectric, but D normal is the charge density. Do y'all follow this? Now, we did a backward on this. We started assuming the voltage, then we got the E field, a little trickier. Then we got the D field, and then if we evaluate the D field on the surfaces of either plate, we get the charge density, right? We're almost there. We need the total charge on one plate to get the capacity still. Y'all follow me on this? What's going to be the total charge on one plate? If we have the D field as the charge density, we'll do this per meter too, right? I think they want capacitance per meter. I assume. Let's do that over here. This is a great problem. So, how would you get it? Well, you would say the total charge on a single plate would be equal to what? It'd be a double integral of the charge density over the defined surface, right? And actually, that's a scalar ds, or you could use dA if you want, but I'm saying charge density is scalar. Y'all with me, class? So now, when I take a look at this plate, what I'm really taking a look at, I'll try to draw this so you can see this well. When I look at the surface of this plate right here, that's A and that is B. You can see that goes on forever, but we want it per meter. So this is the differential surface here. I hope you can see that. This would be ds. Can you all follow me on that? All right, it's going to have a d rho. Do you all agree with that? That would be the radial component in this direction. And it's going to have a dz, isn't it? Y'all see that? Flat plate, right? So you can say that ds here, when I look at this, I can say this is really a double integral. And here I can put the charge density, which is that, which is epsilon v naught over phi times rho. So I can put the charge density, erase this right here. So I can work through here. So that's the charge density, which is epsilon naught v naught over phi rho. Now I have to put ds, which is just going to be equal to d rho dz. Y'all follow me on why I'm doing what I'm doing? How many understand this right? You're very quiet today, so I'm suspicious. There's some concern on my part. I mean, really, just think about this. It's an odd problem. You're not used to doing this type of problem. In the past, we've always looked at concentric spherical surfaces and cylindrical surfaces. This is one where we have planes. Y'all with me? Now, when I look at rho, where does rho go from? If we want the charge density, class, that's the radius. From A to B. And where does dz go from? Remember, it's per meter, from anywhere, how about 0 to anywhere plus 1? Y'all follow me, class? So it go from 0 to 1. That's inconsequential. So that means the total charge on one plate is going to be equal to, well, when I look at this, when I integrate dz from 0 to 1, I get 1, so I don't care about this. Then I take epsilon naught, v naught out here. Phi is the actual angular difference. It's probably measured in radians, if I don't miss my guess, because I think it needs to be, but this is just the angular difference between the plates. And then when I integrate 1 over rho, what do I get, class? 1 over rho d rho? Natural log of rho. You have to evaluate between the upper and lower. That's the charge. You all agree with that? So finally, we go ahead and get the capacitance per meter, and we use the standard equation that the charge on a system of parallel plates is equal to the capacitance times the voltage difference between the plates. Here we assume voltage. You all remember that? And then we got the E field, then we got the D field, and finally, you have charge density and then total charge on a plate. So if you look at this, capacitance is equal to Q over V. Here, that's Q. When we divide it by V, we get it equal to epsilon naught. I'm just going to divide this, and this would be per meter. Epsilon naught, and the V naught goes away because that was the assumed value. So this would be V naught here. And then it's going to be epsilon naught over the angular difference times the natural log of B over A. And I have a comment on that. By the way, can you confirm that is the right answer? It is? Now, the tricky part about this is getting the E field as a function of rho. You have to realize when he says ignore fringing, what he's really saying is the E field is only in the phi direction. And it is not a function of angle. It has to be the same magnitude all the way through there. From it at angle 0 all the way to the other plate. Y'all with me, class? How many have seen a problem like this in physics? Physicists love these kind of problems. You have? No. Nobody? This is kind of a classic problem. They like parallel plates, plates at an angle. They like spherical surfaces. Then they like cones where you have one conic section and another one flared bigger for capacitance. Those are classic physics problems that you get. Okay, so that's the answer. Y'all with me? Now, one question that I have. We're going to get to a few places today. If that's the capacitance, what would the energy be stored in that capacitor if there's a voltage V? Anybody know? Say it again. You hear that? He's absolutely right. The actual energy in a capacitor, this would be energy. I'm saying this for a reason. Would be equal to 1/2 CV squared. That voltage that I'm showing you is the voltage difference between the two plates. That'll always work. That's something you learn in circuits and physics, right? Y'all remember that? It's important to know that. You'll notice that the energy is directly proportional to the amount of capacitance between the plates, but it's also directly proportional to the square of the voltage. Anyway, and what that means is you double the voltage, you take the energy by a factor of 4. Y'all follow me, class? It's real important that you understand this basic relationship. So now, another problem. Thank you for that problem. I'm going to get to some things that will make it more clear in a little bit. Any other questions? That's a good, very good problem. That's one that throws people, and I know Dr. Bashir is from MIT, and I've had students come in, woe is me, or I have to solve things in cylindrical coordinates that I don't like. I remember that's one of his classic problems. That and conic sections. We'll get to. You know what I'm talking about, Dr. Bashir? I know Bashir. He's a very bright guy, very good guy. But I know he drives kids nuts with his random course, from what I've heard. Okay. Next. Anything else before I get going? How many tried some of these problems? You didn't have any other questions? Did you? You got a question?
Yeah.
Go ahead.
3.76.
Okay, hold on, let me erase. By the way, are the solutions up there for this? I want to know.
Yes.
Okay. If the solutions are up there, I think good. But I'll tell you, sometimes the solutions aren't real clear what he's doing. Sometimes they are. Okay. Problem number again?
3.76.
Go ahead.
An inhomogeneous dielectric fills a parallel plate capacitor.
Okay. This is one of the irritating ones. So here we have a parallel plate capacitor with epsilon that is not a constant value. All right, it's a function of space. So what is the value?
3 times the quantity 1 plus z,
1 plus c, go ahead.
where z is measured from the bottom plate in centimeters.
All right, so that's the z direction. This is the bottom plate. Go ahead.
And the surface area of the
Well,
capacitor.
just 3? That's epsilon relative, is it?
Oh yeah, that's epsilon relative.
Yeah, okay. We're going to change this in a sec. Yeah.
The thickness is 1 centimeter, surface area is 50 centimeters squared.
All right, we have a parallel plate capacitor. The area of this thing, area of a plate here. Say that again.
Area is 50 centimeters squared.
And what is the spacing?
The thickness of the capacitor
Yeah.
is 1 centimeter.
All right, I'm going to tell you something that's going to hopefully is useful. Now, normally the only way you can ignore fringing, normally, this is not in your book, but if this is a parallel plate capacitor, it looks like this. You can all imagine, right? Think of an ice cream sandwich. The brown cracker is really going to be the plates. The ice cream is going to be the dielectric. With me? When you have something like this, if you just assume for a second that this is actually a square plate, all right? That means a single dimension on this thing. Now, listen to me carefully on this. Let's just call this L, all right? L itself would be equal to the square root of A. You all follow me on that? If it's square, L times L would be the area. You agree with that? Square root of that would be L. For a capacitor to look like a parallel plate capacitor, you can ignore fringing. This has to be true. And actually, the value I'm going to give you is a little, it should be even larger, but normally what they say is L, right here, has to be greater than, usually a lot greater than S, but it's usually L has to be greater than 10S. Now, that's if you want to ignore fringing. What I'm really saying is that's a very thin structure. What I'm saying is if you look the length of one of those edges on that plate, you know, the parallel plates, that edge will be at least 10 times the spacing between the two plates. Y'all follow me, class? If that's not the case, then fringing becomes a factor. It can be a significant factor. Y'all with me? And this is just a rule of thumb. I'm just curious if he managed to do that. If you take square root of 50, what do you get? Square root of 49 is 7, isn't it? So if you take 7, right? 7 is getting on the order of about 7 centimeters. Would be, it's getting close to 10 times 1 centimeter, right? But it's still small. It's not 10, it should be greater than that. So this problem, one thing I'm going to tell you is this problem would have fringing. I'm going to understand at least what I'm getting at here. Normally you want, when you say parallel plate, you want the plates, or any dimension of the plate, is at least 10 times the separation distance between, at least, typically 50 to 100 times for a parallel plate capacitor to work. By the way, since we're on capacitance, has anybody ever had to make a capacitor in a laboratory setting or anything like that? Anybody? What did you do?
It was like a physics lab, and I can't remember exactly, to be honest, but we were
Here's
like,
Here's the classic thing. Now, I guess they don't do it. Usually capacitors, a lot of them back in the day when they were trying to make them cheap. What they do is there are two plates, but it doesn't matter about the geometry. They just have to be separated by that dielectric and have a constant spacing, all right? So what they do is take aluminum foil, sheet, maybe a couple meters long piece of aluminum foil, put it down, and then they'll put wax paper, exactly the same, actually a little like wax paper on top of that. And then they'll take some aluminum foil that'll be slightly, I guess, thinner, so that there'll be no, the actual wax paper will insulate the inner from the outer one, so they put it on there. Then they take that and they roll it up. They put a very thin rod, tape it on there, and they roll the thing up into a log. Maybe 50, maybe 100 rolls. Follow me on that? And then they go ahead and connect the wire to the inner. Now, aluminum is a little tough to connect to, but there's ways. You've got alligator clamps, so it's easy to do. Clamp it with one, clamp the other one, and they charge it up. And then, usually say maybe 100 volts. Take that 100 volts to C, and they'll take it and you discharge. The kids are shocked. I made a capacitor. That is a capacitor. But if you keep upping the voltage, all of a sudden, you're going to bust through the wax paper. That's called breakdown. Has anybody ever blown up a capacitor? You have? You have? In the labs, I've seen kids do this on purpose. It's loud. Now, I'm just going to give you just a bit of information, hopefully get you more interested. How many know what an electrolytic capacitor is? Anybody? Have you heard of it? An electrolytic capacitor stores a huge amount of energy because the relative permittivity is very high. But it is kind of almost a gooey mixture of stuff. And it can store a lot of energy. The reason it does is it orients the dipoles, but the dipoles in there are something that orient physically upward and stretch, right? So there's motion in there. Now, you know what a microwave does, right? It takes H2O molecules, flips them back and forth and heats. Well, it can happen to a dielectric capacitor, or it's called an electrolytic capacitor, so electrolytic capacitor. So they tell you, usually all these warnings, do not have any kind of current in the opposite direction of polarity on this. So you have a plus minus. And if you do, God help you, because they'll blow up. You'll literally start heating that dielectric and they will blow up. And I've seen the aftermath of these in large capacitors. It can be lethal if you're close by. That basically is something that it's almost like microwave heating. When you try to put current through it the wrong way, the dielectric's sloshing back and forth and heating at an incredible rate, and then it blows up. I'm just giving you an idea of what we're talking about with capacitors. Those are just the standard everyday. These electrolytic capacitors are used for power supplies. Now, you know what a full wave bridge rectifier is, right? When you come off a full wave bridge, you have ripple. You have a little bit of ripple voltage. It's impossible not to get rid of. So what they'll do is they'll put a capacitor, a big old electrolytic capacitor that will never change its polarity in parallel with the output of the actual full wave rectifier. Then they'll put an inductor in series. Now, an inductor always smooths out the waveform, all right? And then on the end of it, it's called a pi filter. They'll put another large capacitor, but that one's usually not an electrolytic. It can be, but it usually isn't. Does anybody know what a pi filter is? Anybody in here? You do? Or not? Anybody at all? No? You know what a full wave bridge is, right? Okay. You'll find out about those things in time. Now I've said all that. So now I'm going to do this problem. All right, I said a whole lot to get, now I'm going to get back to this problem, but I really want to give you that insight. When we're doing this, he says in centimeters, right? I don't like centimeters. If that's in centimeters, how do you make it in meters? You know that. Well, 1 meter is 100 centimeters, right? How about we divide by 100 right here for precision? You agree with that, class? Great. That's right, we're working meters. Divide by 100. All right, that's epsilon relative. Epsilon relative does not have any units at all. Now over here, he said his spacing is 1 centimeter, right? Right. Oh. I'm sorry, I'm wrong on that. This should be, I believe, if we're in meters, it would be 100 Z here, if it's centimeters. 1 centimeter is what? It's 1 over 100 meters, right? 10 to the minus 1 meters. So I'm putting this in meters. So this would be 10 to the minus 2 meters. Now I'm doing this for a reason. Because I do not like, I'm being honest, I don't like centimeters. That means I can use epsilon naught as the normal value. Here I can use epsilon naught equal to 8.854 times 10 to the minus 12 farads per meter. Now, with this particular problem, the value of epsilon changes. Y'all follow me? Here's how we do this problem. We're going to assume a charge Q, and I'll put it right here. I don't know how we did it. We're going to assume Q. Then we're going to get rho s, which is equal to Q over the area. He's given us the area, so if that's centimeters squared, that would be what? 50 times 10 to the minus 4 meters squared. Do you agree with that, class? I'm just putting this down. Do y'all agree? I always do my problems in MKS units. I've been bitten doing them in doing them in the English units or dealing with centimeters and all that stuff, so I always go to MKS first. So I've assumed, here's the way I'm going to do it. I'm going to assume Q, it doesn't matter what it is. I get this rho s, right? Now rho s is equal to the d field. With me on this, class? On the surface of a good conductor, it's equal to the d field. So that means this, rho s, is going to be the d field. Or what I can say is d normal is equal to Q over A. Now, the d field between the two plates is not a function of epsilon. Do y'all follow me? You'll see the method. This is not that tough. Because the d field doesn't vary anywhere between the plates, that's it. D normal would be in actually the z direction. I can go ahead and say that the normal component of the d field, or the d field itself, would just be Q over the area in the, since I'm going to assume the bottom one's going to have a positive charge right here, and the upper one's going to have negative charge, I can go ahead and say this is going to be simply Q over A in the AZ direction. The units, again, are going to be coulombs per meter squared because I'm not going to deal with that. Now, if I have the D field, remember I assume charge, I got the D field, my next step is going to be to get the E field. Y'all with me? I get the E field by doing what? Simply divide by epsilon. So I say that's equal to Q over A, and there's my epsilon, which is 3 plus 100 Z, and then it would be in the AZ direction. Finally, how do I get the value of the voltage? Remember, I assume charge. Once I get voltage, I've got the capacitance. Do you all agree with that? What do I do, class?
Would it be 3 plus 300 Z? If you carry out 3.
Oh, I'm so sorry. Yeah, let me put the 3 outside. I'm sorry about that. You okay with that, everyone? All right, now, once I have that to get the total voltage, what do I do? Integrate it, right? And if I integrate that to get the voltage, what do I get? I find the voltage, remember, strict positive is going to be an integral of E dot dl from the upper, or from the lower to the upper plate. I don't really care about the signage here, so I have Q over 3A, and then I have the integral of 1 over 1 plus 100z, and it's going to be AZ, and then it's dot simply DZ AZ from 0 to S. Now, that means it's going to be Q over 3A. And what's the integral of this? When I go ahead and integrate dz over 1 plus 100z dz, what is that going to be from 0 to S? What do you do, class? Don't you change variables? Isn't that right? What do? You make what? U be equal to 1 plus 100z. And if you take a look at that, then du is what? 100 dz, correct, class? You understand what I'm doing, right? I'm just trying to solve this integration I have here. So that means this is going to be the integral of dz is du over 100. And then I have 1 over u, and I go from 0, or really since u is that, I'm going to go from 1 to S, which is going to be 1 plus 100S. So that's a natural log, so I have 1 over 100, and I have the natural log here of 1 plus 100S, and S is 10 to the minus 2. It's really 2, isn't it, class? If S is equal to 10 to the minus 2, that's going to be 1. So I can replace that by 1 there. 1 plus 1 is 2. So I can just say this is equal to 1 over 100, natural log of 2. And that means this, the voltage here, when I do this integration, this is this integration right there I just did, I get 1 over 100, natural log of 2. And if that's the voltage to get the capacitance, I know that Q is equal to C times V, or C is equal to Q over V. I assume charge, when I divide by voltage, I get 1 over, and that's going to be natural log of 2, right? And then it's over, it's per A, so the A's go away. So it's going to be over, well, it's times A actually, and it's going to be times 300. And that would be farads. Is that what he has? Or not? US, right? Is that what he has in a solution? Didn't I post these things? Can you look it up there? Is that it? It's going to be of that form. He may put A down as whatever that. My A is what? 50 times 10 minus 4. If you put that in there, you should get the right answer. Does he have of the form of 1 over the natural log of 2? He does? I don't know. He does? Is that the answer he has? He probably puts in A. Huh?
3 times epsilon naught A.
Oh, hold on. You know, I'm sorry. I forgot. E is this, right? It's D over epsilon naught. My bad. There should be an epsilon naught. There should be an epsilon naught here too. And I'm sorry. That's sloppy. Is that it? Back there? He's going to have an epsilon naught in that one. Trust me, you'll have a log 2 in the denominator, right? This will be the right answer. That's the method used. Let me just do one thing. I wanted to get through boundary conditions. Answer your question, at least in part. That's not a hard problem. The irritating part is he puts it in centimeters. It's just assuming the charge density, or assuming the charge, get charge density, get the E field, after you have the E field, get E field, and integrate the E field from the bottom to the top plate, get voltage, and then Q is CV, solve for C. All right, I want to go through a couple things. I got waylaid with this thing. So this is the section on boundary conditions if you look in his book. Just take a look for a second. This is boundary conditions. And when I say boundary conditions, it means what happens is at the interface between two different materials. We always assume a planar material. We'll call this material 1 and this material 2. Now, for this point, I'm going to try to keep it simple. So really there are two boundary conditions. The first boundary condition for electrostatics, and this is an important one, is that the tangent E field in region 1 is the tangent E field in region 2. Now I have to make sure you understand, and I'll go through how come that's so. The tangent, if you have any surface, like if you talk about the surface, say this carpeted area standing, the tangent means parallel to the surface or in the plane of the surface. Y'all with me? Normal means perpendicular to the surface or straight up. Y'all follow? Now, when I take a look at this, this will always be true, and here's the reason why. And I'm going to make it real simple. Let's assume that we have an E field in region 1, and we're going to assume that E field is the same everywhere in region 1, or media 1. Then we have another E field down here in region 2. Y'all with me? Now the tangent E field in region 1 would be this value, whatever it is. It would be E1 tangent. Can you all follow me on that? The tangent field in region 2 would be this value. It would just be the projection of this in this direction. Y'all with me, class? That's how you would get it. Just think about the projection on the plane. Now I'm going to come over here, and the next thing I'm going to do, say medium 1, medium 2. If I say I have a path that looks like this, this is going to be a path right here. And what I'm going to do is say, well, I know I have an E field in region 1, or region 2, pardon me, and I have an E field in region 1. As such, I'm going to let this be H, and I'm going to let this be L. So it's a rectangular surface where H is perpendicular to the surface that separates the two regions, and L is parallel to it. Now you know that the integral of E dot dl between, and I'll say between A and B with a minus sign is equal to VB minus VA, right? What's this value? Between A and A. Think about back in the day when you had physics. If you started, say I'm just talking about the work done by gravity. If I start with a point here, I lift this thing up, move it over here, bring it down, move it over, and bring it back to the point it started at. How much work did gravity do? How much work did I do? 0. The path. These are called conservative fields. The path defines the actual value. I'm sorry, the endpoints define the value, not the path. The integral of E dot dl over any closed path, this is the symbol for a closed path, is always 0 if it's an electrostatic field. So it's 0. So look over here. When I take a look at that integration, if I take the limit as that H, which is going to be the spacing above and below, goes to 0, of the integral of E dot dl around the closed loop, it's 0. Think about it. If I start here, and I move, and I'm just going to go over this path integral, and end up at the same point. With me? It'll be 0. Now, the tangent field down here, we know it's just E tan 2, right? It's times L. This integration is meaningless because we're going to let H go to 0. This integration will have a negative sense to it, right? So this integral right here, and I'm about out of time, I can tell, is going to be, and I'll call it E1, or I'm sorry, E2 tangent times L minus E1 tangent times L equals 0. And thus you can say the tangent field of region 1 is the tangent field of region 2. I'm out of time. Next time I'll do the normal field, but I'm just going to say this. If it's a good conductor, D normal 1 is the charge density. And if there is no charge density, but there are two dielectric regions, the normal component of the D field on one side is the normal component of the D field on the other side. Okay, I'll see you Friday. Quiz will be on capacitive/resistance, or both. Do y'all hear me? Make sure you do this stuff that I give because this will help you actually get some more problems.
What if they're different magnitudes?
The projection on this the field is different at the surface. The tangent component, tangent is a projection in plane. Tangent component of the field on one side is equal to the tangent component on the other. That is literally a forced condition. It cannot not be true because even the voltage is not 0.